Welcome to AI Frontiers, where cutting-edge developments shaping the future of technology are explored. Today's episode delves into the dynamic and transformative field of robotics, a domain that intersects computer science, mechanical engineering, and electrical engineering. Robotics has evolved far beyond its origins in industrial manufacturing to become integral in sectors like healthcare, transportation, agriculture, and domestic settings. This episode synthesizes findings from research papers published on May 15, 2025, offering a comprehensive overview of the current state of robotics research. These papers highlight remarkable progress and persistent challenges as researchers strive to create intelligent, adaptable, and reliable robotic systems. The goal is to unpack dominant themes, groundbreaking findings, and innovative methodologies defining this rapidly advancing field while pointing toward promising future research directions. Robotics represents one of the most dynamic and transformative fields in modern technology, encompassing disciplines ranging from mechanical engineering to artificial intelligence. At its core, this field focuses on developing machines capable of perceiving their environment, making decisions, and performing physical actions autonomously or semi-autonomously. The significance of robotics extends far beyond academic interest, impacting numerous aspects of daily life and industrial operations. In manufacturing facilities, robots have revolutionized production lines by increasing efficiency while maintaining consistent quality. Beyond traditional manufacturing, robotic systems assist surgeons in healthcare. Autonomous delivery robots navigate urban environments. Agricultural robots optimize crop management, and autonomous vehicles transform transportation infrastructure. Each application demonstrates how robotics addresses real-world challenges while pushing the boundaries of what machines can achieve. Papers analyzed from May 15, 2025, showcase advancements across multiple domains, reflecting the evolution toward more sophisticated, adaptable, and practical solutions. Among the prominent themes in recent robotics research is motion prediction and planning, where sophisticated models anticipate and execute complex movements. For instance, FlowDreamer, developed by Jun Guo et al., utilizes three-dimensional scene flow to predict future visual observations based on past frames and robot actions. This approach represents significant progress in how robots understand and interact with changing environments. By separating motion prediction from visual rendering, FlowDreamer achieves improvements in semantic similarity, pixel quality, and manipulation success rates. Such advancements enable robots to perform more sophisticated tasks in unstructured settings, marking a fundamental shift in visual world modeling for robot manipulation. Task allocation and collision avoidance constitute another crucial theme, particularly relevant in multi-robot systems operating in industrial environments. Radhan Chandrashit et al. Propose a novel spatial clustering method that divides workspaces into distinct operational zones, effectively solving task distribution and preventing collisions simultaneously. This framework combines k-means clustering for task site division with the 2-opt algorithm for route scheduling, achieving up to 93% reduction in processing time while eliminating persistent collision points. These results demonstrate remarkable improvements in computational efficiency and solution quality, making the approach highly influential for future research in industrial automation. Enhancing robotic perception and environmental understanding represents a third major theme in robotics research. Lemon mapping, introduced by Liji Wang et al., optimizes large-scale point cloud merging through robust loop processing and spatial bundle adjustment. This framework reduces map divergence and improves global consistency, addressing long-standing challenges in multi-robot collaboration and precise localization. By introducing innovations like enhanced pose graph optimization, lemon mapping establishes new standards for geometric quality in merged point cloud maps. Validation across multiple datasets demonstrates superior performance, highlighting the potential of hybrid approaches that combine geometric modeling with machine learning techniques. The recent collection of robotics papers reveals several groundbreaking results that redefine robotic system capabilities. FlowDreamer demonstrates a 7% enhancement in semantic similarity, an 11% improvement in pixel quality, and a 6% increase in manipulation success rates. These metrics indicate a fundamental shift in how robots predict and interact with environments. In multi-robot systems, a novel spatial clustering framework achieves unprecedented efficiency gains, reducing processing time by up to 93% while eliminating collision points. Autonomous surface vehicles trained using deep reinforcement learning show resilience in real-world conditions, bridging the gap between simulation and deployment. These findings collectively establish new benchmarks for performance and reliability in real-world applications. Several common methodologies emerge from recent robotics research, reflecting both established practices and emerging trends. Deep learning architectures, particularly U-nets and diffusion models, are prevalent for complex prediction tasks like motion prediction and visual rendering. Optimization techniques such as spatial clustering and bundle adjustment methods appear frequently, offering efficiency gains in task allocation and map optimization. Reinforcement learning and imitation learning frameworks, including variations like adversarial motion priors and action priors, enable efficient exploration, allow robots to learn complex behaviors while maintaining exploration capabilities. Hybrid approaches combining geometric modeling with machine learning techniques are increasingly common, producing superior results but introducing additional complexity. The choice of methodology depends on application requirements, available resources, and trade-offs between computational efficiency and performance accuracy. FlowDreamer, developed by Jun Guo et al., revolutionizes visual world modeling by separating motion prediction from visual rendering, using 3D scene flow as an explicit intermediate representation. The system begins with a U-net structure predicting 3D scene flow from past frames and action conditions, followed by a diffusion model generating future frames. This modular design allows for end-to-end trading while maintaining interpretability. Experiments across 4 benchmarks demonstrate significant improvements in semantic similarity, pixel quality, and success rates in robot manipulation tasks. FlowDreamer represents a paradigm shift in visual world modeling, suggesting that explicit motion representations lead to more accurate and interpretable predictions in complex scenarios. Madhanchandra Shit et al. Present a landmark study titled Multi-Robot Task Allocation for Homogeneous Tasks with Collision Avoidance via Spatial Clustering. Their framework introduces a novel spatial clustering method dividing workspaces into operational zones for each robot, unifying task allocation and collision avoidance. Combining k-means clustering with the 2-opt algorithm for route scheduling achieves up to 93% reduction in processing time, while eliminating collision points. This achievement maintains high solution quality while dramatically improving computational performance. The theoretical analysis provides valuable insights into how spatial partitioning addresses multi-robot coordination challenges, making this work highly influential for future research in industrial automation. Lemon mapping, developed by Li Wang et al., addresses the challenge of creating globally consistent maps from multiple robot sources. The framework introduces 3 key innovations: robust loop processing, spatial bundle adjustment, and enhanced pose graph optimization. The loop processing mechanism handles outliers while maintaining valid loop closures, while spatial bundle adjustment reduces divergence in overlapping areas. Final pose graph optimization leverages refined constraints to extend local accuracy to the global map scale. Validation across multiple datasets demonstrates superior performance in mapping accuracy and reduction of map divergence. Lemon mapping represents a substantial advance in multi-robot mapping, providing scalable solutions for large-scale collaborative tasks and establishing new standards for geometric quality. Looking ahead, the collective body of research from May 15, 2025, highlights significant strides while grappling with persistent challenges. Integrated solutions addressing multiple aspects of robotic operations simultaneously exemplify progress, as seen in spatial clustering frameworks unifying task allocation and collision avoidance. FlowDreamer showcases how separating motion prediction from visual rendering leads to more accurate world models. However, challenges remain, including computational demands of advanced machine learning models and bridging the simulation to reality gap. Promising directions include integrating geometric modeling with machine learning, hybrid approaches combining expert knowledge with autonomous learning, and emphasizing unsupervised and semi-supervised learning methods. These trends suggest more adaptive, efficient, and practical robotic systems will emerge in the coming years. This presentation was created using GPT Qwen, specifically the qwen-max model, with TTS synthesis via Deepgram and images generated using Grok. While human-reviewed, it acknowledges potential oversights and provides references for further exploration. The synthesis process aims to distill complex research into accessible insights while maintaining technical accuracy and academic rigor. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive.org.